Welcome. Since we were teaching spherical coordinates this week in calculus, I thought it would be nice to talk about the Mandelbulb set, which uses spherical coordinates to be defined. Very excited about this object since quite a few years because it is the YouTube star. It's one of the most beautiful objects which I know. And but I take the opportunity to take a little bit, step back and look at this notion of Mandelbrot topic, or Mandelbulb topic, or more general Mandelstuff. So you can do that very generally when you have some space on which you have some power operation, and you have also a metric, right? So define a map which takes the point, takes it to the dth power, and adds a parameter c, which is also in that space. You need kind of a plus, and you need also a plus. You need also a group operation. So one of the kind of cases which is very natural is if you take a division algebra like R or C or the quaternions or the octonions. In that case, you have kind of just a natural power. And then you can, more generally, even if you have a normed ring, you can define the Mandelbrot set as just all the parameters such that 0 doesn't escape to infinity. And this can be defined even more generally if you don't have a ring structure, but just a power. And this is actually this Mandelbulb story is if you take a parametrization of the sphere, so your space is Rm, and you have a parametrization of the sphere, like the usual parametrization of we have of the two-dimensional sphere, and then you have a power operation which takes the radius, takes it to the power d, and then also every angle, every parameter you have here is just multiplied by d. So that's not very, natural in the sense that this is not a power in some ring. In any normed ring, you can define this Mandelbrot or Mandelstuff, and that works even in a finite ring. If you just say, well, you can also compactify the space. In this case, you can just take infinity, add infinity, and then you have a sphere. And so also here you can just take a point which you call infinity, and that even can be generalized even more if you have just some dynamical system and you have 2 points. You just look where all the parameters, so it's parametrized. So you have parametrized, kind of a parametrized, family of dynamical systems, and you just look at all parameters such that one point doesn't reach the other point infinity. So one point is 0, one point is infinity. So it's a very general, dynamical system framework, and so there's a nice theory in the case of the complex numbers, which I have just kind of here a little bit the history. It's now more than 100 years old, 105 years old, this story. Actually, if you take Cayley, it would even be 130 years old. Cayley was looking at the Newton map already, but complex dynamics, it's started with 1917 with Fatou and Julia, and then some Kleinian group guys, mathematicians, have looked at the Mandelbrot set, or type of Mandelbrot, something similar to the Mandelbrot set, which is actually believed to be equivalent, and then Mandelbrot kind of made this very famous fractal geometry of nature. Others have also had ideas about this, and Douady and Hubbard have proved a very nice theorem already 2 years after that. Hubbard might have even looked at it also earlier. This theorem is that the Mandelbrot set which you have here, this Mandelbrot set is connected, and that's a very, very nice result. And unfortunately, there is nothing like this known for this beautiful Mandelbulb. Maybe I show a picture or movie or animation of this Mandelbulb. I have rendered that a couple of times. I'm actually rendering it right now. An older rendering which I have done last winter for an extension course. I always come back. There's a beautiful program which allows you to zoom in, and the Mandelbulber, and so here is a kind of an animation maybe I also can kind of try out to be with in that space. And currently I'm running something with a kind of golden texture, but that takes about 30 days, I think. But maybe I showed just a movie which I have until now. So here we are zooming into that Mandelbulb. And the most popular choice of where it really already looks good is the case d is equal to 8. But maybe I just show also some other degree Mandelbrot sets and Mandelbulb sets. What is actually very nice is, and it's due to the parametrization, so it depends on the parametrization which you use. It's a little bit confusing because at different places it's stated differently, but definitely the parametrization which Paul Nylander and Daniel White are using is kind of not the standard parametrization which we use. We use here the cosine and here the sinus. So what we have here is kind of a situation where when you are on the equator is actually just phi is equal to 0. So that's a nice situation, because it's a nice case, because in this case the equator stays the same. So if you cut that Mandelbulb at z is equal to 0, so we cut it with z is equal to 0 here, you take the Mandelbulb and you cut it at z is equal to 0, you get the complex Mandelbrot set of degree d. And this is known to be connected. So there is an indication that this should be connected, because that slice that we talk about, a lot about slices in calculus, right? You slice the object at z is equal to 0. It's also called a trace. The question is now, what happens when in general, is this still connected? And that's an interesting problem, and I don't think anybody has looked at it. You might ask yourself, why does nobody look at that? My theory is there are two reasons. First of all, this definition came about, was about then zoomed in 2007, 2009. That's about 15 years old now. That's not, depends on the parametrization which you are using. So it's not a very natural thing here, because what you do is you essentially take the universal lift of the parameter plane, but that's not corresponding here to that thing. So that's related to the fact that you don't have a multiplication on the sphere in 3 dimensions. You have a multiplication on the sphere in 4 dimensions, and that would give you then the quaternion Mandelbrot set, which is actually not so interesting because it's just rotating the usual Mandelbrot set around. For that one now, the Mandelbrot set is not so interesting. There's more interesting in the Julia sets there, and that's something which also in Mathematica has for a long time been implemented, and Povray has implemented this for a long time. That's definitely much before this Mandelbulb story. The Mandelbulb story is particularly kind of popular in the case of R3, because that's a space we live in. And especially nice is also the kind of the degree equal to 8 gives kind of already nice pictures. The equal to 2 case, where the slice, when you slice it at z is equal to 0, you get the Mandelbrot set. So that's very nice, and so that's unknown whether it's connected. I believe it's connected if you look at the pictures, and you make, also because the slice here, right, if you look at the slice, that's connected by Douady Hubbard, and so you expect that to be connected too. But you cannot use the tools from complex analysis. So the tools of complex analysis, maybe just to see, one of the questions is, can you push through this Douady Hubbard proof? I learned this proof at ETH in a seminar of Jürgen Moser, who kind of has a small group, like a freshman seminar here, and every student was presenting things. I was presenting something in higher dimensional complex dynamics, which was really exciting, a theorem of Rabinowitz. And Jochen Denzler, one of my friends, one of my colleagues in ETH, who was writing his thesis with Moser later, would actually present the story of, that was about, I think, 1984. He was presenting that proof of, I learned it from that seminar, that proof, and I have written it down for a course in 2015 here. No, 2005. Here, that's already 17 years for a dynamical system course. It's still on my website, the write-up, but it's essentially it's the proof of Douady and Hubbard. But maybe if we just go through, so that's something which is kind of nice if you have a complex, what you have is kind of, you have a hyperbolic fixed point, so you can linearize it. So that's kind of like a Groman-Hartmann type thing, but their linearization is even analytic. So you have you can explicitly give the conjugation to the z to the d. And so that's then called the Böttcher function. That plays an important role. And then there are some kind of a background thing which comes from Julia and Fatou, not interacting very well. I think they were fighting even. But now they are kind of joined together. The Julia set and then the Fatou set is the complement of the Julia set. And then there is the filled-in Julia set, which contains the Julia set and the bounded components. The bounded components of the Fatou set. And then outside this filled-in Julia set, you have a green function. So you essentially charge that set and you look what the potential values are. And this also can be written down explicitly. So this is called the Böttcher function. And that's kind of the idea of Douady and Hubbard. That's a genius idea. You kind of extend this green function. Yeah, that's not so surprising, right? You can actually extend this green function more and more by just, kind of using the dynamics to define it in a more narrow neighborhood of the Mandelbrot set. But then you can define, that's kind of like a Turing kind of hack. Like the Turing machine which you feed to itself, the universal Turing machine which you feed to itself. You feed the parameter values itself to the green function, and then you get a map which is actually kind of an analytic map from the complement diffeomorphism, from the complement of the Mandelbrot set to the complement of the disk. So that's pretty cool. One would like to extend this even to the boundary, but that's not known. That's kind of the local connectivity of the Mandelbrot set is the big open problem in that field. Here I have kind of a couple of kind of definitions. So local connectivity, there are local versions of connectivity, and global versions of connectivity have nothing to do with each other. So you can have things which are connected but not locally connected, like this devil comp, the sine 1 over x function, or you can have things which are connected but not even locally simply connected even path connected but not locally simply connected, which is this union of infinitely many rings accumulating at some points. There's interesting topology coming here into this Mandelstuff story, and I stop here.